This is the second video in a series that I'm making to support a course in abstract linear algebra. And since we're working everything abstractly and carefully with proofs, that means we are required to do a bit of background information very carefully before we define the typical objects of studying in a linear algebra class. And we're still looking over that background right now. So in the last video, we looked at functions, injective functions, surjective functions, and bijective functions. And today we want to look at invertibility of functions as well as permutations. So we say that a function f from a to b is invertible if there exists another function g from b to a such that if you compose f composed with g, you get the identity on b. Whereas if you do g composed with f, you get the identity on a. You might say, well, why do we have different sets here? Well, that's because the input of f is a, and then its output is b, which goes into g, whose output is a. So that means we need an a here, and likewise we need a b here. Okay, so for our first result, we'll show that if f is invertible, then its inverse is unique. So over here, this function g would be called an inverse of f. And so what we want to show is that we can actually replace that word and with the word the. We have only a single inverse, and we'll write, well, f inverse like that. Okay, so let's look at this proof. So let's suppose that g and h are both inverses of f. Okay, so that gives us quite a bit of information. That tells us that f composed with g is equal to the identity on b, and f composed with h is also the identity on b. Furthermore, g composed with f is the identity on a, and h composed with f is also the identity on a. Okay, so we want to get to the point where g is equal to h. So let's maybe see how we could do that. Well, maybe we could combine these two things together somehow. Let's maybe take this one right here, and we'll compose both sides with g. So that'll give us g composed with f composed with g is equal to just g composed with the identity, which is g, which is also equal to g composed with f composed with h. Okay, so that's starting to look good. So we're not actually going to need this portion of the equality, although it's still true, but we just won't need it for our argument. We'll only need what's happening over here. Okay, so by the associativity of the composition, we see that g is the same thing as g composed with f and then composed with h. But recall, g composed with f is the identity on a, so we have the identity on a composed with h. But then the identity composed with h is just going to be the function h, and so we're done. Notice we've got our function g is equal to our function h, which means that even if we started with two things that looked like inverses, they're really the same inverse. Okay, so we finished proving that this is unique. Now let's prove another result. Now we're going to look at a classic result that says f is an invertible function if and only if f is a bijective function. So let's maybe start with the forward direction. So in other words, we're supposing that f is invertible. That's what we're starting off with. So that means there exists an f inverse from b to a, satisfying these two rules over here. So I'll write it as f composed with f inverse is equal to the identity on b. So I'm just writing these boxed equations over here, but instead of g, I'll write f inverse. And then likewise, we have f inverse composed with f is equal to the identity on a. And now bijectivity represents a function being injective and surjective. And in fact, this invertibility split into two parts, and one of these will imply injectivity and the other one will imply surjectivity. Okay, so let's start with this one over here, which will imply that F is injective. So let's maybe suppose that we have, I'll call them X and Y from our set A, such that F of X is equal to F of Y. So this is the first step always for showing something is injective. The final step, which I'll write in yellow right now, we want to show that this implies that X equals Y. Okay, well, how can we get there? Let's just apply F inverse to both sides of this, and then we're pretty much home free. So by applying F inverse to both sides, we get F inverse composed with F of X is the same thing as F inverse composed with F evaluated at Y, but this left-hand side is equal to X and this right-hand side is equal to Y. And that's because this is the identity function evaluated at X and the identity function evaluated at Y. So we finished the proof over here that F is injective, which means we can hopefully use this equation to show that F is surjective. Okay, so let's get to that. So let's suppose that we have some B from our set B. So our set B is the codomain of F. And so what we want to do is find some little a in A such that F of little a is equal to B. So that would complete the proof of surjectivity. Okay, so how are we going to find that A? Well, let's just take this equation right here, B equals B, and then apply the left-hand side with this F composed with F inverse and the right-hand side with the identity on B. Notice that will give us F of F inverse of B equals B. And that really provides the motivation to set little a equal to F inverse of B, and note that F evaluated at little a is equal to B, which tells us that F is surjective. But now if it's surjective and injective, it's bijective, and that completes this forward direction. Now let's move on to the reverse direction. Now let's prove the reverse direction, and that is if F is bijective, then it's invertible. So let's suppose that F, I'm going to note that we have here from B to A, or from A to B, is bijective. And somehow what we'd like to do is define some function F inverse, which goes from B to A, such that F composed with F inverse is equal to the right stuff. So I'll just put dot, 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 the identity on B in this case, and the opposite composition is the identity on A. So in order to define this F inverse, we need to tell where an element from capital B goes. So let's define, so for maybe little b in capital B, let's say F inverse of B is equal to little a if F of little a is equal to B. Okay, so let's notice that this is possible for all B in B because F is surjective. Notice that's the definition of surjectivity here. If it were not surjective, then we would be able to find a B in B that did not have this rule over here. And then let's notice that it's unique because, and by unique, I mean this choice of A is unique because F is injective. And that's really all there is to it. Notice if we were to try to define F inverse of B to be A prime, for instance, then we would have F of A equals B, but that's the same thing as F of A prime, but then the injectivity will show that A is equal to A prime, and thus we have well definition here. Okay, so now we've proven both of these. Now let's look at some examples. So now let's look at a couple of examples. So the first one is just a linear function. So we've got a function f from R to R defined by f of x equals 3x minus 5. So it's easy to check that this is bijective. That would be some sort of warm-up problem from the last video. Now let's find its inverse. And we can find this inverse using kind of the standard strategy from pre-calculus type class. So let's set y equal to 3x minus 5. That's the first step. And then we swap x's and y's. So we have x equals 3y minus 5. And now we'll solve for y. So that gives us 3y equals x plus 5, which means y equals 1 over 3x plus 5 over 3. And then we'll set f inverse of x equal to 1 over 3x plus 5 over 3. And I should say you can check this easily is the inverse function by doing the composition. I'll let you guys do that. Then maybe another example. Let's define g, and let's define it from r to the open interval 0 to infinity, where g of x is equal to e to the x. And then this has an inverse function, g inverse, which goes from the open interval 0 to infinity to the real numbers, which is the natural log. So g inverse of x is equal to the natural log of x. Good. So there are a couple of definitions. Now let's move on to talking about permutations. Now that we've got a feel for invertible functions and their relation to bijections, we want to look at permutations on a finite set of elements. So let's define this bracket n symbol to mean all of the natural numbers between 1 and n. So in other words, 1, 2, 3, all the way up to n. Then next, we'll define s sub n. So this is the set of all permutations on n letters in this case. This will be sigma, which goes from this set bracket n to bracket n, where sigma is a bijection. But if sigma is a bijection, then it's invertible from what we just got done proving. Now let's look at the following observation, which we will not prove. I think these are fairly straightforward to see. So first of all, the identity is in Sn. Well, the identity is most definitely a bijection. In other words, it is 1 to 1 and onto. So that would just be the function that takes 1 to itself, 2 to itself, 3 to itself, all the way up into itself. Next, if sigma and mu are in Sn, then the composition, sigma composed with mu, is also in Sn. This follows from something that we did last time where we proved that the composition of two bijections was indeed another bijection. Next, if sigma is in Sn, then sigma inverse is in Sn. Again, this comes from something we just got done proving. If sigma is a bijection, then it's invertible. But if it's invertible, it has an inverse. But its inverse also has an inverse, which is back to itself. But that means its inverse is a bijection, so we're back inside of this set. Finally, there's one more little counting problem. And that is that the number of elements in this set Sn is equal to n factorial. And we can count that just by remembering that each of these guys, 1, 2, 3 up to n, must be mapped to a distinct element 1, 2, 3 up to n. So if we start with 1, there are n choices of places to send 1. And then if we move to 2, there are n minus 1 choices because we've used up one of the ones with n, or one of the ones with 1, and then for 3 there's n minus 2, so on and so forth, all the way down to 1, and then by the multiplicative rule for counting we get n times n minus 1 all the way down, or n factorial. Okay, so now let's look at some examples. So I'm going to write these examples using two different kind of notations, and we'll have kind of a nicer notation in just a second. So let's say we're working in S4 for now. So 1, 2, 3, 4, and then I'll put 1, 2, 3, 4 here. And we could define a permutation just by these arrows here. So this means that our permutation takes 1 to 2, 2 to 1, and then let's say it takes 3 to 3 and 4 to 4. So in other words, we have sigma from 4 to 4. In other words, 1, 2, 3, 4 to 1, 2, 3, 4. And we have sigma. Let's put a sigma here to make sure we know that that's how we're defining this. Sigma evaluated at 1 is 2. Sigma evaluated at 2 is 1. Sigma evaluated at 3 is 3. Finally, sigma evaluated at 4 is 4. That's how we can read this chart right here. Now let's look at another one, maybe mu, we could call this one. And let's say it's on S4 again, but now this one does something slightly different. Let's say it maps 1 to 2, 2 to 3, 3 to 4, and then 4 all the way back to 1. So something like that. So now mu is going to go from n to n again, just like sigma did. But now mu1 is 2, mu2 is 3, mu3 is 4, and mu4 is 1. So we could like think about this one as kind of a nice loop. So we could put 1, 2, 3, 4 around in a circle, and this is the action mu on those numbers. Whereas here, we can think of 1, 2, 3, 4 being in a line, and sigma swaps 1 and 2, but then takes 3 and 4 to themselves. So that's another way of visualizing this. One more way to do it is with an array. This is maybe one of the first more standard ways of writing it, and that would be sigma is defined, well, first of all, in the first row, we just put 1, 2, 3, 4. And then in the second row, right under 1, we put where 1 is sent. So this would be 2, 1, 3, 4. Again, because sigma of 1 is 2, sigma of 2 is 1, so on and so forth. And we can do the same thing over here. So mu, 1, 2, 3, 4 in the first row, and then 2, 3, 4, 1 in the second row. Okay, so let's keep those permutations in mind, and on the next board, we'll talk about their composition. So in the last board, we were working with the following 2 permutations, and now let's think about how to compose them. So let's do sigma composed with mu. So that means mu is acting first, and sigma is acting second, because we always move from right to left using composition of functions. So we can do this by writing mu at the top, writing the array for mu at the top. So 1, 2, 3, 4. And then here we have 2, 3, 4, 1. And that represents 1 being sent to 2, 2 to 3, 3 to 4, 4 to 1. That's like going through mu first. And then in the third row, we can exhibit the action of sigma. So we know that 2 is sent to 1, so we'd put a 1 here. We know 3 is sent to itself, we could put a 3 here. Let's see, we know 4 is sent to itself, we put a 4 here. And then we know 1 is sent to 2, so we'd put a 2 here. Then we'd forget about what's happening in the middle. So maybe forget about what's happening in the middle, and then we've got our final description of sigma composed with mu. So it takes 1 to itself, 2 to 3, 3 to 4, and then 4 back to 2, like that. Then maybe as a little warm-up exercise, let's calculate what mu composed with sigma is using the same strategy. And now that we've done this, I want to look at a little bit more of an efficient way of writing these permutations down. Okay, so let's talk our way through it, and then we'll look at some examples. So I'll take this permutation here, written in array notation, and rewrite it in cycle notation. So cycle notation involves just a single row vector looking object, but it's not a vector, it's a map. It's just a way of writing one of these permutations down. So you'll start with the number 1, and then you'll look at your permutation and ask, where is 1 sent? So 1 is sent to 2, so that we exhibit that sending of 1 to 2 by putting 2 to the right of 1. Then we go and look at where 2 is sent. So 2 is sent back to 1. So we would not put a 1 to the right of that. That's not how we would exhibit 2 being sent back to 1, because 1 has already been written here. We would exhibit that as closing these parentheses. So we would read this portion right here as the permutation that swaps 1 and 2. Now we would pick up with the smallest number that is not within this 2 cycle in this case. That would be the number 3. Look where 3 is sent. It's sent to itself. That means we would close this up. And then we would start with the number 4. 4 is sent to itself. That means we would close this up. But whenever we have numbers by themselves, we generally don't write them. So we would just write 1, 2. So this would be the permutation 1, 2. So this is also known as a 2 cycle. So it's a 2 cycle because there are 2 entries. And 2 cycles have an important name, which is a transposition. That's because we're transposing the number 1 and 2. Okay, so let's look at our example over here, our mu. So we'll start with 1. We'll look and see that 1 is sent to 2, so that means we write a 2 here. And then 2 is sent to 3, we'll write a 3 here. 3 is sent to 4, we'll write a 4 to the right of that. And then 4 is sent back to 1, that means we close this up. That completes the loop. Oh, and while we're at it, let's notice that this is a 4 cycle. And this is a 4 cycle because there are 4 entries. Okay, now let's maybe calculate the composition of these two. So let's do sigma, or let's maybe do mu composed with sigma, because that's opposite of what we had on the last board. So here we can write this 1, 2, 3, 4 composed with 1, 2. Now again, these are functions, so we want to think about moving things from the right to the left. So let's start with the number 1 and see what happens to the number 1. So maybe we'll write it underneath for a warm-up in a different color. So if we start with the number 1 here, as it passes through this first cycle, it becomes the number 2. As it passes through this, it becomes the number 3. That's just how we read these cycles. 1 is sent to 2, 2 is sent to 3. So that means in the end, 1 is sent to 3. Now we move on to 3. So let's notice under this map, 3 is sent to itself, so there's no worries. And then under this map, 3 is sent to 4. So that means we would put a 4 here. And now we would move on to 4. So let's notice on the first map, 4 is sent to itself. And then on the second map, 4 is sent back to 1 because it makes this loop. So since 4 is sent back to 1, we would close this into a finished 3 cycle. And then notice that nothing has happened with the number 2. Now we should check that 2 is sent to itself, and thus we don't have to write it down, just to make sure we haven't made any mistakes. So under this, 2 is sent to 1. Then under this, 1 is sent back to 2, so it checks out 2 is sent to itself. So now that we're well acquainted with permutations, I'm going to give you guys a couple of results which we will not prove. We'll prove them like if you ever take an abstract algebra course. They're important to have for linear algebra, but not so important to look at the proofs. So let's clean up the board and then review those results. So like I said, we're going to look at a couple of results that we won't prove, but they're important to define some functions in linear algebra later. You'll see the careful proofs of these in an abstract algebra class. So the first of which is that every permutation can be written as a product of transpositions. The proof of this is actually quite easy. We just won't do it here for time. Here's an example. We have a 1, 2, 3, 4, 5 cycle. So this is the cycle that takes 2 to 3, 3 to 5, 5 to 9, 9 to 7, and 7 back to 2. And that can be written as the product of the following transpositions. And this decomposition of transpositions is not unique. We could sneak, for instance, a copy of 1, 2, 1, 2 in the middle here, since those multiply out to 1. So anyway, we've got the transposition 2, 3, 3, 5, 5, 9, and 9, 7. You can check that both of those permutations are the same. And like I said, this product is not unique, but something is unique about this product, and that is the number of transpositions that this is expressed as. So that is written in the second result. The number of transpositions used to write a permutation is always even or always odd. So we can write this permutation here as a bunch of different types of decompositions into transpositions, but the number of transpositions in this case will always be even. And that's because here we have it written as 4 transpositions, and 4 is an even number. So that motivates the following function. It's called the signum function. and it goes from Sn to the set plus minus 1. And it's like a measurement of evenness or oddness. So we say signum of sigma is 1 if sigma can be written as a product of an even number of transpositions. And then it's -1 if it can be written as a product of an odd number of transpositions. Notice this is a well-defined function by this result right here, the always evenness or the always oddness. So I'll leave you guys with some warm-up problems and then we'll be done. Okay, so I'm going to leave you guys with 3 warm-up problems. The first is to determine the signum of this product of a 4-cycle and a 3-cycle. So we have 1, 3, 5, 7, and then 2, 4, 6. So in other words, determine if this can be written as a product of an even or odd number of transpositions. The next one is to simplify the product of these 2 4 cycles in this case. So by simplify, I mean write it as a product of disjoint cycles. So let's notice that these 2 cycles are not disjoint. They all contain the numbers 1, 2, and 4. So using inspiration from a previous example where we simplified the composition of permutations using the cycle notation, you can simplify this as well. And the final warm-up problem is to write the following permutation 3 different ways with transpositions. And that's a good place to stop.